Today we're doing curve sketching, this time with rational functions. Everything starts the exact same though. To find x and y intercepts, I need to set the fraction equal to 0 for x-intercepts, plug in 0 for y-intercepts. So the first thing I would suggest doing would be to factor both the top and bottom of this equation. And what you're going to find in this case is you'll be able to factor the top to be x minus 3 and x plus 3, and the bottom to be x minus 2, x plus 2. So to find the x-intercepts, that means I set this whole thing equal to 0. That means just the top part equals 0, so x minus 3 equals 0, x plus 3 equals 0. That means my x values will be 3 and negative 3. So write them as ordered pairs, negative 3, 0, and positive 3, 0. For the y-intercept, all I'm going to do is I'm going to plug in 0. When I do that, I should get negative 18 over negative 4, which will reduce to 9 over 2. 9 halves, which would be about 4.5. Not about 4.5, exactly 4.5. All right, horizontal and vertical asymptotes. Horizontal asymptote, we're first going to look at the coefficient of, look at the degree of the top and the bottom. Since they are the same, then we look at the coefficients. The coefficients here, 2 over 1, is your horizontal asymptote. So it's the line y equals 2. Vertical asymptotes happen when the denominator equals 0. So that happens when x equals 2 and negative 2. So then to find the domain, all we look at is where we have these domain issues at the asymptotes. We need to include everything but those two numbers. So negative infinity to negative 2, 2 to infinity, or negative 2 to 2, and then 2 to infinity. That's everything for the original function. Now we have to take the derivative. And as you probably guessed, we have a fraction, so we need to be doing the quotient rule. So we're going to take the derivative low times d high minus high times d low all over low squared. So the whole thing, x squared minus 4, is squared. Okay, from there, I'm just going to kind of simplify. I'm going to distribute here and get 4x cubed minus 16x for the first part. Then here I'm going to have a minus 4x cubed and a plus 36x. Still all over x squared minus 4, that whole quantity squared. Simplify once more, I have positive 4x cubed minus 4x cubed, so those will go away, and leave me with negative 16x plus 36x. So that gives me a 20x over this x squared minus 4 quantity squared. What I'm going to do to find the critical points is set that equal to 0. Again, if the whole fraction equals 0, that means just the top is equal to 0. So 20x equals 0, which means x just equals 0. That is my only critical point. And I even know that the point itself will be 0, 9 halves. We figured that out already from our intercept. So what I'm going to do with that now is I need to draw a number line, and I need to plug in, or put into it, my critical numbers. Don't forget, the other thing you must always put in is the asymptotes. So at positive 2 and negative 2, we have asymptotes. We need to check now 1, 2, 3, 4 different regions by plugging into our derivative function. Well, here's something to take a note of. The bottom here is just some number squared. That means no matter what, you're squaring it, you're always going to get a positive number. So we might as well not even worry about the bottom. Look just at the top. So 20 times any negative number is going to give you a negative. So that's why these two values will both be negative. 20 times any positive number will be positive. So this is decreasing, decreasing, increasing, increasing. So right here is going to be a minimum, I should say, a minimum at the point 0, 9 halves, or x equals 0, because it went from decreasing to increasing. There is no minimum. My increasing intervals are from 0 to 2 and from 2 to infinity. And then decreasing is negative infinity to negative 2 and negative 2 to 0. Okay, so that's everything with the first derivative. Now the second derivative. What we're going to get here, we're going to do a quotient rule again. So f double prime of x will equal, I'm going to take the derivative of this guy just because it's in the simplest form. So it's going to be low times d high minus high times d low. Now when I do d low, the derivative of this guy is our good old friend the chain rule. So bring the exponent down in front, keep the inside the same. My new exponent would be the first power, so it's good right there, and then multiply by the inside derivative. Okay, and then the bottom, x squared minus 4 squared also gets squared, so it becomes to the fourth power. So what I'm going to look at now, first off, 99.9% of the time when you try to solve one of these problems here, doing the second derivative and have a chain rule on the bottom, what you're going to notice, I have a common factor in each one of those terms, so I can cancel one out everywhere. Now it makes it a lot easier to go and simplify this. I can now go and distribute through because it's to the first power, so I'll have 20x squared minus 80, and this guy here will be 20 times 2 is 40, times 2 is 80, so negative 80x squared. My denominator is still the same, x squared minus 4 quantity cubed, and this simplifies down to, it would be negative 80 minus 60x squared over x squared minus 4 quantity cubed. To find points of inflection, I'm still going to set this equal to 0. So what I'm going to do is I'm even going to say, well, I can still factor that top part even more. I could pull out like a, what would that be, a negative 20. That would leave me with a 3x squared plus 4. My bottom stays the same, x squared minus 4 quantity cubed. If I set that top equal to 0, as I did here, well, it means that 3x plus 4 equals 0. Or 3x squared, I'm sorry, plus 4 equals 0. That means 3x squared equals negative 4. X squared would equal negative 4 over 3. Well, x squared can never give you a negative number. So that means this doesn't exist. So that means after all that work, there are no points of inflection. However, I still need to draw a line graph. There's no points of inflection to draw, but again, I need to plot my vertical asymptotes. So I need to check something at all three regions. Well, checking 0 will be the easiest, but again, let's take a look at something. If I have a number and I square it, it's going to be negative. I'm sorry, if I take a number and I square it, it's going to be positive. Multiply it by a negative number, it's going to be negative. Subtract something from it, it's still negative. So no matter what, my top is going to be negative. That means I should just check the bottom. If I plug in 0, for example, this would be a negative number cubed would become still negative. So negative divided by negative will give you a positive. So this should be concave up right now. If I plug in a negative 3 or a positive 3, when I square it, it'll be like 9. Subtract 4 gives you 5. When cubing that is still positive. So I get negative over positive, which will give me negative in each of those regions, concave down. So concave up is from negative 2 to 2. Concave down the other two, negative infinity to negative 2, and 2 to infinity. Now we got all the work done. Now it's just time to graph this thing. Start by graphing your asymptotes. Vertical asymptotes are at negative 2 and at positive 2. Is that correct? Yes. Horizontal asymptote happens to be at y equals 2 in this case. So there we have that. Now let's plot some of the points we know. We know 3, 0. We know negative 3, 0. And we know 0, 9 halves, which is 4.5, which is right there. Now that point 0, 9 halves was a minimum, so it should look something like this. And we should also check. We should now check here and see, well, we said it was decreasing to increasing, which it is in that range, and it should be concave up, which again it is. Now, we should also see here that on this side of the asymptote, I should be having something always increasing. So I need to kind of follow my asymptote, go through the point. I can't cross any asymptotes. And then same with this guy. Yeah, on this side it's decreasing. So I should be following the asymptotes, always decreasing, go through the point, just like that. And both of these appear to be concave down. Well, that's what it was supposed to be. So there's a graph of a rational function.